All right. So welcome to Java Futures 2019 edition. So now that we're on a more rapid cadence for developing Java, I have to be more careful about versioning versioning my talks. So this is the 2019 edition. It'll be different next year. So this is how you know I work for Oracle. So don't believe anything I say. Now, there will be a little bit of overlap between the things that Mark talked about and the thing that I'm going to talk about. So I asked your forbearance in advance. Hopefully, I'll put a different perspective on it, and it'll be worth having sat through a second talk. So I want to talk a little bit about evolution in general, language evolution. So Java is getting older. Java's been around more than 20 years. And in those 20 years, it's been declared dead more times than I can count, and yet still not dead. And in fact, still, by some measures, the world's most popular programming platform, and we want that to continue to be the case for a long time. So how do we expect that to happen? It's not going to happen by accident or by luck. We're going to have to do something about that. And our strategy for ensuring that Java remains vibrant is, it's a big secret, right? Stay relevant. Stay relevant to the problems people want to solve. Stay relevant to the hardware people want to run their programs on, and build on the work and the understanding and the knowledge that people have already built up over the last 20 years. So if you've spent the last 5, 10, 20 years becoming an expert Java programmer, well, we want to evolve the language, but we don't want to evolve it in a way that invalidates your experience. We want to build on your experience. This is hard, but it's not impossible. We look at everything through this lens of compatibility. And there are many kinds of compatibility, but I think compatibility is the key that has made Java so successful. Code that was written 20 years ago still just works. And the way we keep our users is by keeping our promises. When you write Java code, it's going to run forever, as long as you follow the rules. Evolving the platform in a way that doesn't break people's code is more work. It's harder. It takes longer. It constrains our options. It brings us to maybe a different answer than we would if we were working on a clean sheet of paper, but it means that we get there in a way that preserves your investment in your code and preserves your investment in your experience and your knowledge rather than invalidates it. And the classic example of that is what we did with generics, right? So when we did generics in Java 5, the prime directive was people have to be able to adopt generics gradually, which means any given class could be generified immediately, later, or never. And if you're a client of a generic class, you could generify or not. And so that meant that a code base could migrate gradually. There wasn't a flag day where everyone has to stop and change their code. We did a similar thing with lambdas, actually in quite a nice way, which was code that was written before lambdas, but that used the idiom of single method interfaces, automatically work with lambdas on day one, right? So we care very much about preserving the investment that people have made in their code and in their expertise. And like I said, this is one of the reasons why evolving the Java platform may take longer than it does for other platforms, because we're trying to do it in a way that we're not going to have to change it again in a year or two. Language features are forever. Right, so when we add a feature to the language, there's very little path for deprecating it. So we have to get it right. You have to get it right the first time. And language features are special in that they interact with each other. With libraries, if you don't like the JSON library you've built, you can either change it or you can make a new JSON library. And the interactions between libraries are relatively limited. I mean, they may share common types like list or date or what have you, but for the most part, they're independent bundles. Language is not that way. Every feature interacts with every other feature, including all the features we're going to write in the future. So my favorite example of pervasive interaction is serialization, right? We did serialization in 1997. And every language feature we've done since then has had to pay tribute to serialization. It's been this ongoing tax. It interacts with everything. So the guiding principle that we've taken, because language features are forever, is if you don't know the right thing to do, do nothing. And we did this with generics, right? We knew in 1995 that Java needed generics. Parametric polymorphism wasn't invented in 1994. It was well understood by then. But we knew that we didn't know how to do it in 1995. So we waited until we knew how to do it in a way that was consistent with the spirit of Java. And what we got was something that was more Java-like and not just something like C++ templates, which we would be unhappy with if that's what we had today. So, every language feature we work on, we look at through the same lens, which is, does this feature make it easier to build and maintain reliable programs? Right? So this is the big picture goal. The individual features, those are interesting, they're fun. As programmers, we love language features. But the big picture goal is this moving us towards a world where it's easier to build and maintain safe, reliable programs? I keep using this word evolve, and I really mean that. I really think that's what's happening. I mean, programming languages exist in an ecosystem, and when the ecosystem you exist in changes, either you have to change or you're going to die out, right? The problems people want to solve are changing. The hardware people want to run on are changing. The techniques people want to use are changing, and we have to change with it. And I think, it should be obvious that there can't be and never will be a perfect programming language because, even if there was, it would have been defined relative to a point in time, to a certain set of problems that were popular, a certain set of hardware that was available, a certain set of programming techniques that were known. And if the problem is changing, the tool that might have been perfect for yesterday's problem won't necessarily be perfect for today's problem. So in this kind of evolutionary model, you can think of programming languages as the predators and programming problems as the food supply, and the state of hardware and software engineering as being the environment, right? And so we have this ecosystem, and rather than talking about a language as being good or bad, I think it's much better, or certainly rather than talking about one language as being better than another, I think it's better to think about whether a language is evolutionarily fit for the the environment that it finds itself in. And if the environment changes and the food supply changes, you're either going to adapt or you're not going to survive. Similarly, developer expectations can also change, and that's part of our ecosystem. We didn't have generics in Java 1.0, and a lot of us learned to trust and enjoy programming in Java without generics. But now, if you look back at some Java code from before Java 5 or Java code before Lambdas, you look at it and you say, yuck, how did we program like that, right? So our own expectations of what's good enough changes as well. So, clearly, we're not done evolving Java. We're never going to be done evolving Java. We need to continue to evolve, to adapt to new problems, to new hardware, to new expectations. And on the one hand, we're never done. On the other hand, you have to be mindful that systems can get full, right? So if you look at what happened to Perl, right, this is a cautionary tale. Perl went through a period of very rapid evolution from Perl 3, 4, 5. Lots of features got added, and there never was and never will be a Perl 6 because it got too full. It became impractical to add anything to it, and it collapsed under the weight of its own complexity. So this is a cautionary tale for a language designer. On the one hand, you have to evolve. On the other hand, if you evolve too haphazardly, you close off your opportunities for evolution. So there's a narrow range of success that we have to navigate our way through. So let's talk about what we're doing in this area. So what's happened in the last year, or maybe a little bit more than a year? We have changed the way we build and deliver Java releases. So starting a little more than a year ago, we moved to a 6-month time-driven release plan. We've delivered more than 2 releases under this plan now, depending on how you count. So we used to do things in these 2 to 4 year feature-driven releases, and this didn't work very well, right? It was difficult to plan. There were often date slips because, big surprise, big problems like lambdas or generics are harder than they look, and they might take longer than you expect. And that turned into a perception that Java was moving slowly. But it also created some distortions that little features got stuck behind the big features. So if we had a 3 or 4 year release, there might have been features that were done in the first 6 months, and they had to wait 3 more years before they saw the light of day, and programmers had to wait 3 years to use them. And that almost made it not worth doing little features because if they felt like they were going to get stuck behind the big ones. It also meant that when you only ship every 3 or 4 years, the release management overhead is very high because you really don't want to take the risk of a feature missing the window and having to wait 3 or 4 more years. And by moving to a more flexible planning process where features get late bound, it's okay to miss the train because the next train is in 6 months. And what that's turned into, and this has been a sort of a big pleasant surprise, is we get to spend all of our time on engineering work and much less time in release planning, which is great because that means we can deliver even more in a 6-month release than we would have been able to otherwise. So we released Java 9, little more than a year ago, and since then we delivered Java 10 and 11 6 months apart on schedule, and Java 12 should be shipping in the next little bit more than a month. And so this seems to be working. It seems to be working in terms of actually delivering on time. It seems to be working in terms of delivering relevant features. And from my perspective, in terms of the amount of time we spend on release management versus engineering, it's a big win as well. And it's also paid some dividends in the way we think about evolving the language. And this was a little more of a surprise, right? So no language feature, well, almost no language feature takes less than 6 months to do, right? So it's not like we can only work on things that take less than 6 months. We can work on things that take 10 years. We only have shipping opportunities every 6 months. But when you were doing a big release where the driver was modules or Lambda or generics, that tended to crowd it out everything else. And so the smaller features just always lost the priority race against the bigger features. And I would say we kind of over-rotated towards bigger features. And the more rapid cadence has given us the opportunity to kind of rebalance that and do a mix of smaller and bigger things. And there are some worthwhile smaller things to do. So I think that's we've moved to a better place. The only downside, of this is on a more rapid cadence, there's a greater risk that something escapes before it's ready. When Lambda took 3 years, there was a lot of opportunity for things to bake that they might have looked good enough, but you think about it for another year and you realize, oh, there's a better way to do that. And so it becomes more critical for us to get feedback from the community on new features early before they are frozen in stone. And we're doing some things to try to encourage that. So as an example of a smaller feature that people have been asking us about for years that kept, just not making the cut was local variable type inference, right? So this is a feature that many languages, many curly brace statically typed languages, Scala, Kotlin, C#, already had. So we knew it was a feature that fit well, in Java, and Java's had type inference for 10 plus years. So it's not like it's a foreign feature to Java. People who've used it in other languages really like it, but somehow it just never got to the top of the priority list. But we did this in Java 10, and the idea is simply that if you have a local variable that has an initializer, you can infer the type of the variable from the type of the initializer. So it's not dynamic typing. It's still the same static typing that we've always had in Java. But if you think this makes your code readable, and this is on you to make this decision, you can lead the type and just say, infer it for me. And the reason I think that it is likely to make some code more readable is that very often there's a lot of redundancy between the type and the variable name. The variable name is actually the part that you pick. You get to pick a variable name based on what a variable does in your program. So if you pick a good name, the type isn't as important. If your names are all terrible, like X2 and Y3, well, your code's going to be unreadable, but it was probably unreadable anyway, so it's not like we made things much worse. So, this is the option but not the obligation to leave out type information in the case where you think the code is perfectly readable without the explicit type. So this comes with some restrictions. This is only for local variables, not for method return types or fields. And a lot of people say, oh, this is just syntactic sugar. It's actually not. It interacts with the type system in a subtle way because there exist some types in Java that are not denotable. What denotable means is you can actually write down the name of the type. String is a denotable type. But there are some types, like anonymous classes or intersections or captures, where you can't actually write down the type of something. You can have an expression of that type, but you can't write it down, and so they get special treatment. So for example, if you say var c equal this dot get class, you would think that the type of that is just class of question, but it's actually a capture type. It's the capture of what question mark means at this particular point in the code. So what this means is this is a feature, like I said, that a lot of people thought was syntax only. It's actually going to force more people to have to deal with some of the dark corners of the Java type system. That's a trade-off we're going to have to deal with. As an example of another non-denotable type, intersection types. If you say list of 1, 2, and then the string 3, you might think that's a list of question. That's really a list of question, extend, serializable, and comparable, because those are the common supertypes between integer and string. There's no free lunch. These types existed in Java all the time. If you don't write down a type, you will get a type. It might not be the type you expect, but that's up to you. So, this was one of the most commonly requested features that we got. On the other hand, when we decided to finally do it, all of these haters came out from the woodwork and said, "Oh, you're going to ruin Java. Oh, you're encouraging people to write bad code. Oh, you're just giving into fashion." Right? You can't win. Right? So what's interesting is, in the months leading up to when we were going to do this, and we said we're going to do this, and everyone perceived, oh my God, this is the last opportunity to stop them from making a terrible mistake. Everybody complained and told us we were doing the wrong thing, and then it shipped, and nobody complained, and a lot of people said they love it. And the disaster of unreadable code that was predicted did not seem to happen. Which just goes to show that nothing's black and white, right? People, when something new comes along, people imagine the worst. They're very vocal about it, and the reality is it's going to be okay usually. And it takes some time for good practices to emerge. Fortunately, someone on our team, Stuart Marks, wrote some very nice documents, a style guide and a frequently asked questions list about this feature that sort of help guide you towards how to use the feature well and how to avoid some of the mistakes. So, go ahead and take a look at those. They're not very long. They're pretty helpful, and use it if it makes sense to you. All right, so now let me talk about some features that are coming soon. Like I said, one of the challenges with the 6-month cadence is that of getting feedback before it's too late. So as language features are forever, and with the shorter releases, there's less bake time, what we've done is we've baked in an extra round of what we call preview, where features go through a round of preview. Preview is it's not really beta, it's not experimental, it's a little bit more than that. It's basically the feature's done. It's fully specified, it's fully implemented, you're going to have tooling support for it, but we have a 6 or maybe 12-month window where we're going to be willing to make small changes. If we get feedback that say, oh, here's something we hadn't anticipated, let's make some tweaks. So it's an opportunity for us to gather feedback, for people to try it out in a broader set of environments than we've been able to, and make a last-minute course correction if necessary. So I encourage people, if they have the time and inclination, to try out features while they're in preview, because that's the time when your feedback is most actionable. And so in order to not accidentally be using a preview feature when you don't know it, you have to opt into it. And there are flags for the compiler and the runtime to enable preview features, and there are options in the IDEs. I'm not sure if, oh yeah, this is nice and readable. Then the IntelliJ language level picker, there's one for 12 and one for 12 preview. It's something where you can try it out on your code and see how it works for you. So the preview feature that we're shipping in 12 is some enhancements to the switch construct. And there's actually two enhancements here. One is the ability for switch to be an expression, and the other is a more sensible way to write your switches, and you can use them independently or together. We looked at a lot of code where people had used switch statements and discovered, not surprisingly, that the majority of them are actually expressions in disguise. But since switch can't be an expression, people simulated expressions by having a variable, and in each arm of the switch, you stuff a value in that variable. Well, we hope, right? And so that's a little bit of a roundabout thing to do, and it's error prone. You can forget to break. You can forget to stuff, the value in the variable in one of the arms. And we had already been looking at enhancements to switch as part of a larger project called pattern matching. And we sort of recognized that, well, that feature's not ready, but some smaller pieces of it are, and we factored them out and were able to ship it early that are generally useful to everyone. So here's an example of a switch statement that's being simulating an expression. So you declare a local variable, and then you have a bunch of cases that stuff something into the variable. And then at the end, you have to have a default clause, even though there's only 7 days in the week and you've covered them all. So there's a lot of repetition here, right? There's the repetition of the assignment. There's this unfortunate need to break on every case. And then there's this need to handle the default. And those are all things that I would put in the category of opportunity to make a mistake. And we don't want to give you opportunities to make mistakes if we can avoid it, right? So here's what it looks like with a switch expression. First of all, note immediately, it's a lot smaller. It's also a lot more obvious, and it's less error prone. I mean, this is kind of the code you had in your head when you sat down to write it, the previous code in the first place, but you couldn't write this code, so you ended up having to write the other code. But this is very straightforward. You don't have to break. You can't forget to handle a case. You can't forget to yield up a value. And if you're switching over something that we know is a sealed domain, like an enum, the compiler doesn't force you to write a default. It knows that you've covered everything. If you don't cover everything, it will tell you, oh, you didn't cover Saturday. So this shows sort of both of the new sub-features of switch as an expression, and the new form of case labels that let you say, do one thing per case, which is a very common situation with switch. And like I said, you can use these independently, statement versus expression, old style labels, new style labels. You can use either or both. So, this is, like I said, something that we worked on in the context of pattern matching. So when pattern matching is ready, there will also be nice integration of switch with pattern matching. But in the code that we looked at, something like 60 to 80% of the switch statements could be profitably refactored into something simpler and more reliable. So, we think that's a nice improvement. All right, so what else is going on? There's a lot going on. Mark talked about a lot of projects that we're working on: Amber, Valhalla, Loom, Panama, and others. I'm not going to talk about all of them. I'm going to talk about two of them, Amber and Valhalla. And in particular, I'm not even going to talk about all the features in all of them. I'm just going to give an overview. But the upshot of this is our feature pipeline is amazing right now, and this is, I think, is another side benefit of the more rapid cadence. It used to be when you did a big feature like Lambda, by the time you ship 8, you have nothing left in the pipeline. Everything that you've been working on, you just shipped. And after sleeping for a month, then around comes the project manager with their clipboard saying, so what have we got for 9? And you don't really have any ideas because you just shipped everything you had. We will never be in that situation again. We have so much that we're working on, and we have a lot of flexibility about how we package it and when and how we slice it up. It's really a nice thing. So Project Amber is about productivity features. They're the sort of smaller features that programmers really like because they're close to the code. And there's a lot of things going on: pattern matching, better ways to declare classes, sealed types. I'll talk about a few of them. So pattern matching is a technique that people generally associate with functional languages, but that's mostly accidental. The functional languages embraced pattern matching early, but there's nothing about pattern matching that's specific to functional languages. It works nicely in object-oriented languages too. And the observation is there are 3 things that we tend to do together all the time when we write programs. You ask a question about an object. are you a string? And then you make a conditional, you do something conditionally on whether that was true or not. If it was a string, cast it to a string and get some property out of it. And then usually when you extract things, you want to put them somewhere, like in a variable, right? So what pattern matching does is fuse these three things: a test, a conditional extraction, and possibly one or more bindings into one operation. So if you have code like this where you say, if object instance of integer, then cast it to integer and do something with it. So you'll note immediately there's some repetition here. And this is irritating to type, right? It's needless boilerplate. But it's also an opportunity to make a mistake, right? You just tested it was an integer. The only sensible next thing you would do is cast it to an integer. But if you have to do that explicitly, you might cast it to the wrong thing because you were cutting and pasting from something else, right? So it doesn't actually add any value, but it gives you an opportunity to make a mistake. That's a bad balance, right? So we'd like to eliminate that redundancy. And there's lots of ways to get there, and we think the richest way to get there is pattern matching. And so if we take that code and we turn it into a pattern, so a type pattern is there's many kinds of patterns, but the simplest pattern is a type pattern, is a type name and a variable name. Looks almost like a declaration, not by accident. And if we put one of those on the right side of instance of, where we say if object instance of integer int value, what that means is test if it's an integer. If so, cast it to integer, bind that cast value to the variable that you just named, and then in the middle there, you can just use it. Now, not only have you eliminated the redundancy, but you've eliminated the chance for error. And there's other kinds of patterns too. Type patterns are just the simplest, but one of the immediate benefits is almost every cast in every class everywhere will just go away, because it will be, you can just turn the instance of cast into a pattern, and you don't need to do the cast. But this actually interacts nicely with a lot of other features. So for example, we have short circuiting and operations in Java. And if you look at the code for a typical equals method, no one ever writes them, right? Everyone just says to the IDE, please generate this for me. And like the equals code that your IDE generates for it, is this a shining example of beautifully structured code? No, it's a mess. It has nasty control flow. It's a mess. And by restructuring equals test to use pattern matching, we can turn our equality implementation into a single expression where you say, if the other thing is an instance of this class, and do the implicit casting, and then a short circuit and his state is equal to my state. These methods become not only more compact, but they become more readable and less error prone. So this is, this works out pretty nicely. And we can do patterns and switches too, right? So here's an example of a chain of if-then-else statements that logically wants to be a switch, but never could be. Right? And so we have all this repetition. There's the repetition I talked about, which is instance of then cast. And then we have the repetition of asking, are you an integer? Are you a long? Are you a double? And then we have the repetition of, well, then, do something with it and stick it in the value. And with pattern matching and the feature I was just talking about, expression switch, we can make this code much more straightforward and much less error prone. So here's what this code would look like with a statement switch using pattern matching, where I can put a pattern to the right of the case. I say case integer I, that means is it an integer? If so, cast it to integer, bind that integer to I, and then I just use I in the in the rest of that case. Now, this is still a switch statement, so I'm still operating by mutation and still breaking. So that's, I would say we're not done yet. But if we combine that with an expression switch, we now get some code that's a lot more readable, a lot smaller, a lot less error prone, and frankly, the code that you had in your head when you sat down to write this stuff in the first place. So pattern matching is not just about stealing a feature from another language that looks cool, although it is cool, and other languages have been there first, and that's okay. We're willing to let others do some of the trailblazing and make some of the mistakes and learn from those mistakes. It's about being able to express things more straightforwardly so that you don't have to make these error-prone, circuitous ways of expressing yourself. Now, pattern matching is actually a rabbit hole that goes very deep. I'm going to go very quickly through a couple of examples just to give you an idea of like where we're going in a few years, way down the road. But this is not, but there's a big story here. So I talked about how patterns are combining a test, an extraction, and binding. So what other things do we do this with? Well, we do this with when you say, is something an instance of some domain object like circle? Well, then what are you going to do? You're going to extract the components of the circle, the center and the radius. And pattern matching can fuse both of those. All right, so in this example, I have a deconstruction pattern for circle, where I say if shape instance of circle, and then I have an argument list. And you can think of this as the opposite of a constructor. A constructor takes some state and makes an object. A deconstructor takes an object and breaks it back up into its state. And this fuses the are you a circle? If so, cast it to circle, and then get the center and the radius, and I'll use type inference so I don't have to write the types down explicitly, and then I can just use it. And this isn't magic. Deconstruction patterns are just class members like constructors. They're actually the dual of constructors. We're not doing any kind of magic guessing of like, oh, center is a field name, so I'm going to pluck that out. And none of that is going on. So classes designed for deconstruction would provide a deconstructor. And that, just like they provide a constructor today. And, in some sense, we've been coding around the absence of pattern matching in our language for years and haven't even realized it. There's a lot of APIs out there where you call one method to say, are you a foo? And then you call some other method that only works if it's a foo. And here you have an opportunity to make the mistake of calling the second method without having called the first method, and then you get an exception, right? So for example, in the class Java-lang class, you can say, does this class describe an array? And you can say, get me the component type. And you can call getComponentType on a non-array class, and you get an exception or null or some other unexpected behavior. But really, these two methods should have been one API point in the first place, because you should only ever call them together. And if they had been written as a pattern, if we had patterns 25 years ago, it would have been written something like we have up here, if a class instance of array class var component type, and you do the test and the extraction all at once. So this opens up new opportunities for API designers as well. So here's one more example, and this doesn't even go to the bottom of the rabbit hole. This just sort of illustrates one of the nice ways you can use this. Imagine you have a shape type, and it has subtypes for circle and rectangle, and a circle has a center and a radius, and a rectangle has 2 points, and you want to compute the area. So let's assume that these things have deconstruction patterns for testing and extracting their components. And I can switch over them, saying switch on the shape. Are you a circle? If so, extract your center and radius and compute pi r squared. Are you a rectangle? If so, extract the 2 points and compute delta y, delta x. And if this is a sealed type, when we have sealed types, we won't even have to say default here. So this is less code and less casting and all of that than the way we do this today. And you might ask, how did these classes get declared? And I'll just sort of show you one way that they might be declared in the future, where you declare the shape interface and you say that it's sealed, and that means it can only have a specific set of subtypes. It's only the ones I'm declaring here, no other subtypes. And that allows me to case exhaustively over them. And record, what's record mean? That's a way of declaring a class that is just a dumb holder for some state. So a point is just x, y. A circle is just center and radius. And so I've declared circle and rect to be subtypes of shape, and they automatically get constructor, deconstructor equals hash code, accessors, everything like that. So the combination of sealed types and records might also be called sum types and product types, might also be called algebraic data types. This is a construct that has been understood in programming languages for a long time. It's not going to eliminate all the boilerplate of all Java classes, but it will eliminate a lot of the boilerplate of a lot of Java classes, and that's a good thing. Last Ambra feature I want to talk about really quickly. How many people here use string.format to write the toString method of your objects? How many people don't use string.format because you heard a rumor that it's slow? Not too many. OK, that's good. So pretend you forgot what I just said. I hear all the time people saying, oh, I don't want to use string.format because it's really slow. And it actually is really slow. And it's slow for an obvious reason. It uses var args, so it's taking the ints, the primitives, and boxing them into wrappers, and then boxing the arguments into an array. And then the format string is almost always a constant, but it gets reinterpreted every time. So we've looked through the JDK to find there's like a dozen or so methods that are sort of pathologically bad in this way. And we have some targeted compiler intrinsics for them, like string.format. The upshot is string.format gets like 50 times faster. So, the reason that we invest in doing this is because we don't want to give people the bad choice of doing the readable thing or the fast thing. We want to make the readable thing be the fast thing, so people will just write the correct code the first time and not feel guilty about it. So we're also doing some interesting performance work. So speaking about performance work, the last section here is about Project Valhalla. Mark talked about this a little bit. This is an ambitious project that's been going on for a long time. We've been working on Valhalla almost 5 years. Some of you have heard me talk about it before. Some of you are probably thinking, oh my God, is he still talking about this? It's a big project, and the ambitious goal is no less than rebooting the way the JVM lays out data in memory. And this is important because of massive changes to the underlying hardware in the last 25 years. So 25 years ago, a memory fetch or an arithmetic operation were about the same cost. They were on the order of a few clock cycles. Today, a cache miss can cost you 300 clock cycles, and a i7 can issue 4 arithmetic operations per cycle. So a cache miss can cost you 1,000 instruction issue slots. So if the cost model has drifted by 1,000x over 25 years, chances are, even if where we were was optimal 25 years ago, it's not optimal today. So Java data structures tend to be very pointery. You have small blocks of memory connected by pointers, and the need for this layout is driven by everything as an object, which was a great philosophy in 1995. But it comes with some costs, and the costs weren't so bad in 1995 because of the hardware reality of then, and the cost today, the relative costs are higher, and we've realized in the last 25 years, not everything needs to be an object. And so if you don't need to be, you shouldn't pay the overhead of it. So to illustrate, if we have a class point int x, y, and we have an array of points, and we fill that array in, what we have is the array is an object, it has a header, it has a bunch of slots, and each of those slots holds a pointer. And those pointers point to objects with a header. And so the usable data in this diagram is the x's and y's. The overhead is all those object headers, which is generally two words per object, and the pointers, which is another word per object. So this is like a 250% memory overhead. Now, some developers, when they see this picture, they say, oh my God, I don't want to do that. I will hack up my code to do this. All right, I'm not going to ask if people have done that because people are too embarrassed to admit it, but you know who you are. And you're not forced to do this, but developers do these things anyway, sometimes out of necessity, sometimes not out of necessity, but just because they overvalue performance, even though their program is plenty fast enough. But people do this. And the reason this is bad is this code is less maintainable. It's more error prone. It's forcing the programmer to do more bookkeeping that compilers and VMs are really good at doing for you. Then this stems from the same trade-off that I was talking about with regard to string format, but in a much bigger sense, which is the developer had this choice of pick either abstraction or performance, and they picked performance. And if you don't have to choose, you're more likely to pick the one that leads to more maintainable code. The reason that we had to have that bad layout in the first place is we can never tell whether you're going to use the identity of an object or not, right? Maybe sometime a year from now, you're going to lock on this object. So we have to allow for that possibility and lay things out so that objects have identity. If you're willing to say, I promise, I don't need my identity. I'm just my data, nothing more than that, Then we're able to optimize the layout so that you get the layout that you want, right? So this is the layout that you probably thought you were getting when you said array of x, y points, and were a little bit surprised to find out you were getting a different layout. So the question is, what code should people write to get this layout? And the answer is quite simple. Say, point is a value. Now, what does it mean to be a value? A value is an aggregate with no identity, like ints. Ints are values. What you're saying is there's nothing there but the data. There's no locking. There's no mutation. There's no subclassing. I know exactly what this thing is. It's just these three fields. And that enables the VM to say, OK, well, I know how to flatten that. I know how to flatten that into arrays. I know how to inline that into the layout of objects that hold a point, hold one of these things. So if, our rectangle example earlier, if point were a value type, and I said a rectangle has 2 points, instead of holding 2 pointers to points, it would just lay out x, y, x, y in the rectangle. And because all there is the data, 2 values are equal if they have the same data, right? So you have to give up a few things. Like I said, you have to give up representational polymorphism, which generally means no subclassing. You have to give up mutability. But a lot of us code in a way that doesn't rely heavily on mutability and subclassing anyway. And in exchange for giving these things up, we get routine flattening. We get flat, dense memory layouts. We can get rid of those object headers. And we can get code that behaves like ints rather than like objects. So we have these benefits today for 8 special types: int, long, double, float. So values, unlike primitives, can have almost all the things classes can have. They can have methods, they can have fields, they can have constructors, they can use encapsulation, they can say private, they can have type variables. They just can't have mutability and subclassing. And as a way of understanding how do value types work, ask yourself, well, how do ints work? And value types almost certainly work the same way. So you could think of these as faster objects with some restrictions, or you could think of these as programmable primitives, and both of those ways of thinking about it are correct. And the mantra, as Mark alluded to earlier, is codes like a class works like an int. You sit down, you write a class declaration, it has a name, it has fields, the fields have names, they can have access control, they can have methods, they can have constructors, but then when the VM gets its hands on it, it just gets chewed up and laid out flat in memory and passed on the stack or in registers rather than through the heap, and you get better performance. OK, so there's not a lot of people who are banging on our door saying, give us value types. There's a few. But it's not like every Java programmer in the world is saying the thing Java needs is value types. So how come we're investing all these years and tens of thousands of engineer hours into this project? And the reason is actually everybody wants value types. They just don't know it, right? So they're the bleeding edge application developers. They know it, right? They're working with enormous heaps, big data, machine learning, and they want to fit more data in the heap, and they want more control over memory layout. And with this, they'll be able to have that. They know they want values. But how many people here use, say, Java util hash map? OK, now, none of you have modified hash map, right? But if hash map got faster, you'd be happy, right? And your program would be faster. So libraries can take advantage of value types in their implementation and deliver faster code. And that makes all applications go faster. Classes like optional should be values. Class numerics like big decimal should be values. And so libraries can deliver value-based abstractions or abstractions that use values in their implementation to enable people to write faster programs without even thinking about values. So that's really cool. How many people here program in languages on the JVM that are not called Java? OK, so if you're using JRuby or Kotlin or Scala, these are languages that have made different choices about their type system than Java. Their ints aren't exactly 32 bits, for example. And because their ints aren't exactly 32 bits, they have to do tricks to represent their language runtime in the JVM. So for example, Ruby has arbitrary precision fixed nums. So if something overflows an int, it switches representation to something like big integer. And that means all numerics in Ruby are objects, and they're all paying the penalty of object headers and indirection and all of that. So compiler writers can use value types as a compilation target to implement language semantics that are different from what is built into the JVM without paying that big performance penalty. Languages that have tuples or multiple return can represent these as returning a value rather than having to allocate something on the heap, return that, and unbox it at the call site. And again, most of us are not compiler writers, some of us are, but most of us use compilers every day and would be very happy for the code that compilers generate to be faster. So in the end, value types, even if you never program with them, is going to make every Java every Java program and every program in non-Java languages on the JVM go faster. So that's why we're investing so much in this. So we've been doing this almost 4 years, a little more than almost 5 years. In that time, we've done 5 rounds of prototypes. Each of these prototypes was one of these, let's look at this little slice of the problem and see what we can learn about it. And we're finally at the point where we've covered the whole problem with little slices, and we understand how the pieces fit together. So I would say that this is sort of the transition between the research part of the program and the development part of the program, which is a huge deal. I mean, we knew it was an enormous project when we started, and we've made continuous progress on it. And we're probably aiming at, in the next year and a half to be able to actually deliver something that people can actually try out with their programs. And it won't be everything. It'll be, it'll be a start. But it's really starting to bear fruit now, and it's a really exciting time. So Mark did a demo. I'm just going to briefly recap that and show the results. So imagine you're doing matrix multiplication. And the elements of your matrix are complex. So what do? You write a class complex that has a real and an imaginary field, and then you implement addition and multiplication in the obvious way. And this is all easy and straightforward, except for the part in red, which is unfortunate, where you have to allocate a new complex to represent every intermediate value. And when you scale that up to multiplication, now you're doing the same thing. You're allocating more intermediate results, more intermediate arrays, etc. And so if you run this program, it's going to be dominated by allocation and indirection. If you make a one-line change to this, you change complex from a class to a value class, you've signaled that I don't need any of that indirection. So let the runtime eliminate it all. And the data that we got, and this is like on a laptop class machine, showed the runtime improved by a factor of 12. Okay, which is about what I would have expected given the cost of boxing and such. All the boxing cost has gone away. But something else cool has happened too. And if you dig into the performance data that you get out of your benchmarking framework, one of the numbers that we pulled out was instructions per clock cycle. And remember I was talking before about how modern x86 processor can issue 4 arithmetic operations per clock cycle, but in reality you almost never get that because you're spending all your time waiting for the memory pipeline to cough up data. So in the boxed version, we were getting about 1 instruction per cycle. So we had multiple arithmetic units sitting around waiting for data, and we were only able to actually do 1 instruction per cycle. When we eliminated the memory access bottleneck, we were able to get up to almost 3 times that because we were able to harness the instruction level parallelism in the processor by keeping it fed with data. So that's the goal that we were aiming at. So great, mission accomplished. But and not all applications will see speedups like this because this is one that is completely dominated by data access cost. But data-intensive computations often have this characteristic. So so this is pretty relevant to a lot of problems. So okay, wrapping up. we've got a lot of stuff going on. I've just touched the surface. Amber has already delivered some features. There's a lot more features coming. Valhalla is starting to bear fruit. Panama is starting to bear fruit. Loom is starting to bear fruit. It's a really exciting time. I fully hope and expect that when I come back here next year and give next year's version of this talk, I will have different things to talk about because we will have delivered some of these things. So thank you very much. I'm willing to take questions if we have time. If not, I'll sort of like stand around here and you can all crowd around me and ask questions like will happen anyway. So thank you very much.